is the following. So, as we've mentioned, we consider the spherical category G, and that on the category is a general phenomenon of maybe okay. Let's start with another place. Okay. Okay, so I'll explain this in a moment. This is kind of a phenomenon that has to do with loop groups acting on categories, and here is the basic things we're going to use. So start with V, the representation of Lang's loop group, and consider the following. We consider an Elisa attacking, so which is an object this category, and we specifically know the one from the loop star, and we act on it to the vacuum representation at the critical level. And so the claim is the following, that we obtain a multiple of this representation. This is kind of the definition of taking Frankel. So here's what's going to happen. Let me denote by R the map from overs to stack of local systems, irregularly, it's unramified local systems on the disk, which is the same thing as point for the jet. So therefore, I can view V as a quasi-vector sheet here, and I'll pull it back to here. So yeah, this is a quasi-vector sheet on this affine scheme of regular overs. And now I apply Taken-Frankel, and I think, well, this quasi-vector sheets are the same thing as modulus for the algebra functions, and Taken-Frankel tells me that this algebra function is exactly the center. So this is what we'll need from the Taken-Frankel isomorphism, and this is what governs the number of Cohen-Britton moments. I recap. We act in the vacuum, and what you get is this. So where if the way I view this guy as a module over Z, that's where I use Taken-Frankel. So Z maps to algebra function overs, and so this is view as module algebra function. So that's one thing. You get it's fun. Second thing is the following. So remember that the Hilliard stock is that was in fact a unit in the personalistic category for G. That doesn't tell you the level, and it's also a unit in the representation in the category of all considered representations. There's the category where we don't impose this integrability condition with respect to L plus G. And so Kevin explained that it's a unit, in particular, it's a factorization algebra. Now we probably have this function of Drenko-Sokolow reduction, so it goes from considered representations. That we already just like this basis. And so Kevin explained that if you apply this factorization functor, it sends factorization algebras to factorization algebras. In what was KM? So KM is all different representations. Representations of the
there was a different notation for it.
Or what was it?
I think it was
like just all Kac-Moody representations, but that's otherwise we'll get confused. So now you can see on general grounds that well the center acts by the morphism back in the module acts on the we vacuum vector, so we get on grounds, the map will be Z. So Z is what you think denotes the center. And so the theorem is that this is nice modulus. So it's also the theorem of Hagen and Frankel, different one. And combining the two, you see that this is also the algebra functions of variables. Before, and now let me combine 1 and 2, so let me mention one more thing that's Kevin said. So again, this is a unit in this category. What Kevin explained that property being units in the factorization category, that every object in this category is automatically a factorization module for this factorization algebra. So therefore, when you specify reality, when you apply this function with the S, it can be enhanced. So you take S automatically enhances. To a functor yes, it can that's good. If they not quite, if they wrote closely related, again from Gaitsgory. To the category of factorization modules for Z. Now, well, factorization modules, sorry, to actually say DS back. So this line would have been valid for any level, not necessarily critical. Now we use critical. So this is, as I wrote there, this notice. And this, by taking Frankel, just rewriting vertically what I wrote there, is algebra functions on regular volumes. And now I'm using what Kevin did in his talk. So this category is up to renormalization, exactly the same thing as incoherent sheaves, integral star mirror orthogonals. So we obtain a function from here to here, and in a moment I'll explain words that will turn this functor, something obtained from this functor in the equivalence of patterns. So again, take the upshot of phase talk, the last line is the existence of this functor. And let me just recap what the FLE will say. So the FLE will say that if you pre-compose this, then the resulting functor factors through incoherent sheaves, not just on meromorphic operators, but on monographic free operators. It's a closed subscheme, denote this by IoT over star. So note that we are in the derived categories, even though we have a closed embedding, the direct image is not a fully faithful functor. So this property of factorization of this functor as this is not a property of the vector structure. It's a yes or no question. But we'll prove that, and this functor is what they call the FLE, and we'll show that this functor is in progress. So that's what I want to do in this talk, but we'll see how far I'll get because I'm really restricted by 1 hour. All right, please. Yeah. So yes, so this is the algebra you have. Yeah. But isomorphism 2 is the same as this. Yeah. And the taking Frankel is the same as this. It's algebra function very low. And then what Kevin said, that in this situation, you can affine scheme with the connection, with the factorization modulus to the algebra functions on it. That's exactly the same as category of incoherent sheets of the in scheme of the horizontal sections of the former function is, which is by definition meromorphic open functions. Okay. So that's how we got this. Okay. Yeah.
Is info upper star very different from info lower star?
No, it's just it's the same. It's just I like upper star, Kevin likes lower star.
Okay.
Addition of the stars doesn't matter. All right.
Like this equals to like the translation modules, is this for greater minus infinity or is this like?
You mean this?
Yeah.
Yeah. So this category formula is incomplete. Sorry, if you left completion of that with respect to the destructive. So they are the same on the eventually co-connected parts, like intco and quasico, but they differ at negative infinity.
Then when you take a look, this is not Q-co if you take the. Yeah, like.
So this intco star, because the in scheme differs from qco. Like if we are in the scheme, the completion of intco is qco, but this is an in scheme. And you're getting something very pretty far. So this is what you get, kind of by definition.
So maybe just to add one more word to that. So again, just like Ben's saying, it's like info and partico, absolutely 100% correct. One difference is that info and partico are both sort of good mathematical objects. Here, this info star of operators is the good object, and this factorization model, this left completion is not a good object at all. Like it's not some fundamental thing that's nice. It's just like some pathological thing that should.
It's left completion, but like in cohomological doesn't behave well. It's like we don't know that it's compactly generated. It's a category that with which we don't has cohomologically bad properties.
Yeah. Any question you have, you can run into all sorts of questions about this guy. Is it actually the derived category, the Eulerian category, blah 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 blah. There's any questions you can ask, and they all sort of time on.
All right, so let me try to realize this program. Right. So first of all, something which was hinted at but not explicitly mentioned, we consider the world of categories equipped with an action of the loop roof. So, and in this case, so one fundamental operation that we can do is to take spherical category. It's by definition the category of objects equivariant with respect to the arcs. Example, you can take
a word for people about what.
So means the following: for every point of the group, it has a self-conquer behavior associative. But what do you mean by point? Point is, of course, Grothendieck point, like scheme point with values in a fine scheme. You have to do it all in families. But more than that, so when we talk about strong actions, so replace all I said inside of the group, it's like you group their own. So it's really you're taking points up to decimal. So when C is Km, this split of Km is exactly what will give the note right numbers. I'm not writing G. So other examples, you could take C to be D modules of the loop group. So here you have to work a little bit because of it's of infinite type. It's not a big here. So it acts on itself in left and right translations. Let's say take right translations, then split. Well, LG will be exactly the modules of the Riemann-Grassmannian. So as it should be, and so on and so forth. And what I meant over there is the following. In this situation, LG acts on C, then what we call SPH, which is by definition D modules on LG, on L plus G, on L plus G, will act on SPH. See, it's the usual expected algebra construction. All right. So what else can we do? So like, let me just add here. If you have a category acted by LG, you can take this spherically generated part. So if you wish, it's the minimal subcategory in C, which contains this the spherical category, and which is preserved by the action of G. But you can write it down explicitly. So C, and it was generated. It's a category acted by LG, and you can write down as follows. It's D modules of Riemann-Grassmannian. which is acted on the right, according to what they just wrote by SPA. G tensored with SPA. And so this embeds back using the action to C, and this embedding is fully faithful functor and it makes the right adjoint. All of these functors commute with an action of LG. All right, so there are these generalities. And also you can do the following. So you can create this width Schlick and width star. These are just abstract categories, and you do them by the recipe that was explained in Andreas' talk. So for example, this one is it's a full subcategory in C. It's the limit of intersection of subcategories where we pose a covariance condition with this subgroups and alpha against the character. And this is a quotient category. So it will turn out that for this talk, this will play a more prominent role than this one. So for example, if C is the modulus of the defined Riemannian, what you get is exactly the categories that Andreas introduced. So this is with star G, and similarly with Schlick. All right, and so this category has, well, both have universal properties. This one with respect to mapping in, this one with respect to mapping out. So here in particular is mapping out. So you consider functors to categories with no action on which intertwine the action, specifically the loops of N with your character. Why am I saying this? That we'll consider with star of Gaitsgory, and we're looking at this functor ds enhanced or ds, both. So Gaitsgory 2 int star of meromorphic loopers. And by its construction, this functor intertwines the action of loops of N against the character with the trivial actions here. So this functor factors through. So this is the canonical projection. Let me denote this functor by ds enhanced the bar. Bar stands for something. I'm passing for the quotient. And so here, let me quote a theorem from which the FLE will be deduced. So it's a theorem of Sam. And Sam calls it the affine Skrabin theorem. I have no idea who Skrabin is, apart from the composer, but apparently it's not him.
That's a good name for it.
What?
It's the first student as the first.
Great. So which says that this ds enhanced is an equivalence. So again, it's an important theorem for this talk. So this is an equivalence, and from this we'll bootstrap our FLE. All right. Ask me a question. I want to breathe for a minute. Say again?
Where's the spectrum?
This this functor ds is taking semitic cohomology against loop algebra of N against the character. If you look at it on the nose. If it were just cohomology of Lie algebra, if you translate an element of the group, your cohomology doesn't change because you're killing exactly this Lie algebra, this phenomenon. So I'm taking cohomology specifically with respect to loop algebra of N against the character. It's designed so that it's equivariant against the group N against that character.
So I mean, it starts covariance.
It's coinvariant. Yes, it's the property of coinvariant. But you have to show this functor. Factors of coinvariance. It just does the job. Exactly that. Ask me another question.
Yeah, so suppose I don't know this subject well, so I actually worry about which are, like, are they actually different?
So according to the theorem of your neighbor, they are They are canonical isomorphic, but this theorem is verboten.
Right.
Until Thursday, you can't use it. Okay.
But then various were the historical.
What are these generated patterns?
Say again.
What are these spherical generated patterns? Is it?
I don't know. I mean, it's something. It's something. Well, maybe I know, but it's a full set. It's always it's full set category. Yeah, it's something. Okay, let me proceed. Okay, so now I'll now take this and I'll do something with it, and from this something we'll deduce our FLE. Right. So now I take this and I'll let me apply the operation of taking with star to both sides. And what I obtain is the following. I'm saying that with star of G tensor SFG G with C alpha G. Well, it's isomorphic to with star C spherically generated. So it's not complete tautology like what I did here. Like if I were to write with star of this times of product, it would be tautological from the definition of C spherically generated. What I did here, I dragged with star outside the tensor product. And so this requires a justification, many justifications. So with star is a very nice operation to use with all colimits on tensor products. So that's why it's justified. And so we'll call this equivalent 0. That sits aside with star of C. And so we're gonna play with this extensively. All right. Okay, looking at the cheat sheet, I think I'm tired. All right. So next topic is something that I don't think has been brought up explicitly, but it will play an increasingly important role in the coming days. It's the derived attack equivalence. So
Speaking of things that are verboten, maybe you use the left for instead.
yeah, I just think about it. Right. And you're acting. No, spiritually act on the right with the refinement, but G acts on the left. Okay. It's kind of convolution. So you take the module Heisenberg's one, you can convolve it with the module spherical module, you obtain object C, and it's factors to this.
I mean, as an exercise, you can imagine what happens if you have a representation of a finite group and the sub. And consider the action of corresponding group algebras, and you will have, you will be talking about sub representation generated by invariance with respect to the sub.
Exactly. All right. Right. So now the right from that hasn't come up yet. Now. So first of all, we have the use of attacking, we should note this way. So it was the model function of this attack on the and the right attack is expansion of this function that it makes it actually equivalent. Finally, after a long discussion, we note that we actually stack a counter in the opposite direction. So the base stack goes from relative check here, and this attack, which will be equivalent, go to some other category, which I'll tell you what it is. So you take the following, consider the following fiber plot. Consider log cis regular with respect to G check. Again, on the disk. So this is really point on G check over log cis with itself over log cis mirror one. So, and then you consider interval class. And so for this talk, we're doing everything at the point, and in this case, this is a nice in fact, algebraic stack, which looks as follows. So again, let's set a point
This is point for check. But now you're taking the final point over something horrible, like the static local systems or the functionalistic stuff in nightmare. However, when you take the side product and topologically, you only see the formal. So the formal neighborhood of the image, and the formal neighborhood of the image is perfectly nice. It looks as follows. You take the Lie algebra, you check, you complete it at 0, mod G check. But again, that's what this guy is. But you might as well take the final product without completion 0, it's the same thing. So this is really nice algebraic, the right algebraic set. It's our favorite guy, point as point over G check, and then modulo modulo the transaction. I write int code because it's finite type. I don't have to write in those stars with the. Let me just say that if you want to try to do it over the run space, you run into by n. It's a kind of homological algebra nightmare. So you have to make so these things become wildly infinite type. You have to deal with a lot of like int code theory back with the type. This can be overcome. We just thought it would not be possible to cover in this control. But recently doing this theory will overcome, which covers the interesting aspects of the story, all the more technical ones. Anyways, so you have your interest in info star, and if you don't receive a match just by direct image, it's back to back. Get code from use code that, which is the same. This is as smooth. This is the same as registration.
It's just speaking technical process, are you your spherical category realized?
My theory of categories and all this. That. So just let me emphasize that. So again, this was not explained explicitly in this workshop so far, that what is this guy actually equivalent to? So it's not equivalent to this, but it's equivalent to that. So look how this category looks like. This is a derived stack. It's part of the T structure you can check, but there are highest X that have to do with the derived structure. All right. What of them?
By the way, can I ask you something? What is the level of, what is it? It's an equivalence of minority or one level of?
So it's equivalent of factorization monoidal, is 3. So like so far I wrote over points that's monoidal.
Yeah, and the fact it's the equivalence is a theorem of standard adjustment. What's your last names?
That's for the factorization version, it utilizes as your pattern.
Yeah, so at the point, there's a comic of Finkenberg and written factorization, which is much harder. I'm very curious as whether or not they'll be able to say what I'm intending to say. Let's see. All right. So another definition related to that. So and we do know this category of split G check step. So our different like I said that split G is equivalent to split G check step. It's a nice way to write it. However, this split G check step has monoidal quotient, which we denote G check step temp. So this temp, this motif of being tempered was already appeared in European stock and now, and it will appear again. So what is this guy? So this guy was field code of this nice derived stack, and this guy is body code. This is our usual forget to conquer, or not forget to conquer this. Coarsening conquer because we denote psi from field code classical. And moreover, we have a module category that we call C tilde, in package with a split of something, on which a split G check spec X to it will attach C tilde temp,
when we tensor up. So we temporize it. You will see why I'm introducing this definition in a second. All right. Great. Just 1 second. Uh, did I just erase what scanning? So this is scanning. Well, this is, yeah, I'm erasing it. Version. All right. So now I'll explain the principle of reconstruction, how we go from Scrabble theorem to the FLE. So here's the principle. We consider quasi-co Loxis red, again, which is the same thing. So we have to check. Even in the paper, you never decide which notation we're going to use, so we use both. And just note that it has 2 commuting actions. So one is the split G check spec temp acts on it. And on the other hand, it's a quasi-co Loxis mare, but I don't want to consider this nightmare. I'll consider just the formal completion of that rather regular locus. That's also used there. So it's a bimodal, and in fact, it defines the Moritz equivalence. So it's just easy to see that. So
You're asking why it's a bimodal, these 2 categories.
Because this is exactly endomorphism, so this over this.
What?
But otherwise, we're doing with at the point with a very final dimensional geometry point times point over G, and it's very easy to see.
Okay, you gave an incorrect answer to the previous question. So
It's okay, but it is a bimodal.
which says something about convolution with some like fiber products, or you don't have to
Let me-
write all the formulas, but so people know.
I have that much energy left, just leave it. Let's take it. All right. So, and moreover, it defines the Moritz equivalence between these 2 guys. So you can start with a module over the. So this bimodule defines the Moritz equivalence. And so let me come back to this formula. And so I'll use this like this for the Wharton blackboard for just 1 second. So we'll now. So now remember the geometric custom Mashaleka formula that Andreas introduced. So Andreas said that this is the same as Reggie check. But we're using with star, and naturally, with star is the dual category we treat. So this was invariance, this was covariance, the natural dual to each other. And this category is self-dual. It's a rigid symmetric monodic category self-dual. So you can take the dual of this equivalence, and we call it FLE infinity. So the FLE that we're talking about before, it's FLE at the critical level. That's FLE infinity. So here is a tricky thing. There's the verboten equivalence between Schrick and star, and you can ask if it turns FLE infinity with Castle Mashaleka. The answer is no. It's up to the Chevrolet automorphism. So there's something tricky going on. It has to do with the fact that if you take the double Fourier transform, it's not identity, it's -1. So today we're going to be using this. And so we have this on this we have split G acting. On this we have split G check spec acting. And this is our geometric derived Satake, and it's derived, it's rigged just in the paper of Sam and Justin, it's rigged so that this is equivalent, is compatible with these actions via direct attack. So that's the game. So why am I mentioning this? It's for the following reason. So let's interpret that verboten formula this much. So I'll rewrite, instead of with star, I'll write rep g check. And again, I can't decide if I want rep check or quasi-fold. Loxis reg. Tensor was you check spec with C, and this is with star of C spherically generated. So I just rewrote what's written there, but we already can reap some benefits. And let me denote this formula isomorphism 1. So I just said that this guy is a bimodule for switches spec and quasi-co Loxis meromorphic. So therefore, the left-hand side acquires an action quasi-co Loxis meromorphic. You check completed at the regular locus. So therefore, we have the same thing as here. So we obtain that if you take a category acted on by the loop group, you could take its spherically generated part, and you could take the Whittaker category, it's acted on by this monoidal category. Let's say in parentheses, I don't want to write it, but let me just say it out loud that we expect much more. In fact, it's expect. You could take just arbitrary category acted by LG. If you take its Whittaker category, we expect it to be acted on by quasi-co Loxis meromorphic, the entire thing, not just the formal completion. We don't know how to do it at the moment. So kind of one of the big conjectures of the local language theory, but we can prove a small part again. The small part is that you take not your initial category, but the spherical generated part, and instead of the entire log system meromorphic that we don't understand, we have the formal completion at the regular locus acting. So, okay, so we have this, but I also said that this is a Morita equivalence, so therefore we can almost recover this. And another corollary is that C is incorrectly isomorphic to the following, so you can recover it as quasi-co Loxis reg. You check tensor over this acting agent on the left, Loxis mer. You check formally completed around the regular locus with this guy, which for now is acted on by this. So this is not entirely correct, and the correction is that it's not this, but temp. So temp is introduced here. So, and let me denote this isomorphism too. And I claim that we are almost at the FLE modulo something. Okay. Where are we? So far, so this is what we found. We can check the time. Pardon me? What's it that why you need the completion of free code?
the tensor over this tuple completed at the regular.
You mean here?
Oh, yeah.
So it's that Moritz equivalence.
Oh.
Yeah.
Oh.
All right. So we apply both this and this to C being constant. And let's see what we got. And so what you obtain is the following thing. But so quasi-code looks into check red. Tensor over with what we call characteristic. So it's isomorphic to bit star of the spherically generated part of mixed media, which is a full subcategory in width star of all of mixed media. And now comes our friend Stravic. It says that this is the same as core star of all the homomorphic operas. And one can ask, what is this full subcategory? And here there's a easy lemma that comes from the fact that whatever this category is generated by just KL, and KL has this field generated with file modules. So lemma, instead of this category, under the identification, scrubbing the identification, it's just int co star on of meromorphic operas, but the guys supported at the monodromy locus. So this is, and I emphasize, this is not, it's not monodromy operas. It's like, it's the formal completion of monodromy operas inside all meromorphic operas. It's like incoherent sheets of the entire thing, but set the rate of support. It's really, it's a full subcategory. So we've got that. So this is, that's what we've got by combining Scrabin and this Moritz growth. So Lemma says that.
Because if you say a few words about that lemma, like
Yes. I appreciate something. Just because who there is. So let me say how this monodromy free workers, how they look like. So they split according to co-weights of your G check, which are the same as weights of your additional group of the following thing. You take there's notion of lambda regular over. It's a honest scheme, not an in scheme inside meromorphic overs, and you enlarge it. So you take its formal completion, but inside its formal completion, you cut out the formal subscheme of finite for dimension. That's what it looks like. Importantly, its reduced part is disjointed with this lambda regular overs. And the way you prove it is this, but on the other hand, you have those categories of generators called violin modules. These are particular objects in KL, and so that functor from left to right will essentially ds. Apply this ds to the lambda. So it's a theorem. I don't remember whom, maybe Frankel and stuff. I can't remember. That's okay, good. So it's O on this lambda check, lambda right. So that's where this comes from. Like these guys generating both stuff. Okay, doctor. But I've used my working space. Right, let me erase it a second.
So this MF outside, correct, this looks like,
Pardon me?
the MF outside, correct, that one.
It means that direct support.
So this is like more like a funnel for each other.
Yes. So we're not there yet. And you see, it's tensor over the spherical category with that gives you this what I want the FLE, because I'm not there.
And if you think a little bit about how it's taught, it's exactly the difference between locus reg and the formal completion locus mare on locus reg. Like it's something you're sort of off by a factor if you factor that size.
All right. And what I'm gonna do now, so I have this equivalence, this diagonal one, and now I'm gonna apply isomorphism 2 to it. And so as a corollary, we obtain the following. We obtain that if you take KL, but as acted on by SPH, which is the same as SPH spec, and we take it, we temporize it. You obtain that it's isomorphic to quasi-code Loxius reg tensor over quasi-code Loxius mare, which formally completed with the regular locus, with Ilko star of meromorphic overs with set theoretic support and the monodromic locus. And so recall again what I want. I want the FLE. I want KL to be just Ilko star of monodromic free locus as they are, not some kind of formal completion. So how do we get from one to another? So let's look at the following Cartesian diagram. So I have meromorphic overs formally completed the radial locus, mapping to local systems, meromorphic formally completed the regular locus. Inside, I have the regular locus itself. And inside, by definition, I have the monodromic free overs. So just from this picture, you see that Imco's star of this, but it's just a map of stacks, lives over, it's acted on the quasi-flow of this guy. Just from this picture, you obtain the following. You obtain that, well, it's also, you have to slightly justify because Imco's star what quasi-co, so we have to justify it with the tensor product, but it all works out. Basically, according to what Dima explained, the Imco star of monodromic free is really the tensor product quasi-co Loxius Chapman. Quasi-co Loxius mare, formally completed. Regular locus with Imco's star mare monodromic free locus. So we have this, and we have this, which is this. So look, the right hand sides are the same. Hence, left hand side are the same. We win, we'll hold. We'll hold.
I think in dinner.
What?
Like I think what the content of this, like we have lemma and then long parallel, and if you not understand, it's not.
Oh, the lemma said that this with star of it's Moody, spherical general chart as a full subcategory inside equal star with all meromorphic overs is exactly the condition of having separate support in monodromic free.
So the lemma says that the diagram.
No, the lemma says that this diagonal arrow is an equivalent. So I'm saying that So I have the vertical, I have the horizontal equivalence. Yes. Which sits inside here, and I'm describing the essential image of. There are two reasons why we can't go home yet. Please.
So do you think that a monodromy-free opera is somehow infinitesimally close to a regular opera?
No, I'm not saying that. No, monodromy free operas are the definition of the part of operas that live over regular local systems. This is the Cartesian diagram. And this is a valid equivalence.
So is the upper arrow there an inclusion? It's the arrow.
Yeah. It's monodromy free operas. You get included into their own formal completion inside neuromorphic operas.
Oh, so it's not formal completion along regular, it's from.
Sorry.
That's hard.
That was a
Can you raise the top border?
I can't.
It's not
Oh, should I lower the top?
Yeah, sorry, that was a typo. It's monodromy free.
Okay.
This is regged because we are in local system. So this board is fine, but something else is not fine.
But you're using the KL10, this KL.
Okay, so the two statements I'm using here, note that the corollary recovers KL temp. What I'm after is KL. So proposition, which will be also used tomorrow, is that in fact KL to KL temp is so KL at the critical level specifically is temporary. It's really a remarkable feature of critical level if you are at an integral level where it still acts. It's not true that KL is temporary. Like it's temporary at the critical level. I cannot prove it to the blackboard. It's written in the paper. It's a very nice proof, but nothing complicated. Just don't have time to. Okay. Due to this, I can erase the temp, but like in fact, that our trouble is deeper. So I claim that we're still not done. But who can tell me what the body is? This is pointwise. It is pointwise, but even pointwise we're not done. So here's where the trouble is. When we did this theorem, we used a particular action of this on this. Let's recall what this action was. It came from this vertical identification. And when we said that the action with star of this quasi-co log system error formally completed, it came from this from isomorphism 1. So you remember? So we said that due to isomorphism 1, quasi-co acts. So we use this action to get an action of with star that's smoothly spherically generated using Scrabin. Who knows how to do Scrabin? We moved it to here, and then we got our action here. And for this isomorphism, we use a geometric map from operas to local systems. Here, we suddenly recall that operas, that here, the definition of operas was some kind of dummy. We didn't ever use the fact that they're geometrically connected to local systems. And here, we all of a sudden remember, aha, operas are really something connected to local systems. So what you have to show is that the action of this on this coming from this diagram is the same action as there. So you run into this, and when doing so, well, you have to use something, and it's in fact we'll use exactly the birth of operas, which I thought I would explain, but I won't because I don't have time. So it's another like half an hour chunk of math. And in fact, it's like I really apologize because that was one of the main reasons Kevin gave his talk, because it's beautiful math. It's basically cost-free from the birth of operas as I formulated it if you use enough factorization techniques. Basically, you have to look at the factorization closely enough. Don't do anything, just look at it. Like in factorization will give you exactly these two actions and you agree. And so like it kind of, this proof really demonstrates the power of factorization techniques. But so maybe we'll do it. Maybe we'll try it. So we'll see. Now it's 5 minutes before 6. We have to finish. But like saying this factorization technique allow you to prove pretty non-trivial things. All right.